Welcome. I'm not too sure that at the end of this I can actually make this video go from sideways to the right way up. So I apologise in advance if it's impossible for me to do so with the tools I've got at the moment. Okay, this is just, you can just tilt your head on the side or lie on a pillow. This is just a flat conductor. There we are. It's a flat conductor and it is bent and has a hole in it just there. And this is just a piece of wood which has a pin in it, and I can put on that and I can tilt this and make it move backwards and forwards as a pendulum. To stop that, so to make a car sick. Okay, right here, backwards and forwards. Excuse me. Now, I've got over here, just put it there so you can see it, a bit further back I'd say. You can see I've just got it's got a little magnet on it. That's a neodymium super magnet, and it's attached to this wooden block, so I can put the wooden block there. There's the magnet on the other end, and I can get it really close to this. Okay, it's not touching. No way is it touching. So I'll do it sideways so you can see it firstly. So it's fat fingers in around the road. And I can move it close, and I can set this thing swinging backwards and forwards. Okay, so let's go side on. That's side on. Let's go right way up. I'll just do it again. Right, now, before we start, let's have a look at a little tap. And let's take a few moments to see how long it takes to come to a still. Okay. Now, the only reason why it's actually slowing down is there's a slight bit of friction up the top here with the pin, and that's a source of energy loss because of friction. Right, now I'm going to put the magnet into position. Remember, once again, it is not in any way touching it, and I'm now going to tap. And notice it comes to a halt really quickly. One more time. Now, why does this happen? Well, this is a flat conductor or an extended conductor, and even though this magnet here is not itself would not be causing a changing magnetic field, the motion of the pendulum as it passes through backwards and forwards, this little section just there of the pendulum would perceive itself to have a changing magnetic field. So as it goes through, that section would think the magnet is moving across it. In other words, in its frame of reference, it thinks the magnet is moving backwards and forwards. All you're seeing is my fingers there. From its frame of reference, it sees the magnet is moving. In reality, we know that it's a magnet stationary. It doesn't matter. Either way, the flat conductor perceives a change in magnetic field, and therefore inside on this area of the magnetic field, EMF will be induced. And according to Lenz's law, excuse me, because it's a flat conductor, this is going to be an eddy current, and the size of the eddy current is quite large because it's as large as the area of the magnetic field combining with the that section of the flat conductor. So we'll probably get an eddy current probably as big as my fingernail as it sweeps backwards and forwards. And according to Lenz's law, the direction of this current will be in such a way that it will oppose the change that is causing it. Now, what is the change? The change is the swinging backwards and forwards. So as it swings down, the magnetic field will try to oppose the motion and create a field such that it will keep the motion this direction. In other words, it will try to break it, and that's brake as in B-R-A-K-E, as in a brake pedal on your car. So as it swings this way, it will try to break it again, stop it from going away, and stop it coming off towards. And so as a result, it constantly is pulling and pushing on this pendulum to try and stop it. So as we get there, once again, without it, the only form of braking effect would be from the friction up the top, and this will slowly get in there. But if I wanted to brake it quickly, I would put on a magnetic field. And this is the way that we break the wheels of a train, because the wheels of a train are very large circular flat conductors. We just use an electromagnet, and we turn the electromagnet on when we need it, and it will stop the rotation of the wheels quite quickly. So this is electromagnetic braking in that case. Right, yeah. But remembering, not all the time do we want eddy currents. Sometimes we want eddy currents to be reduced. And here I've got the same comb, exactly the same size and weight and everything, except in this one here has a combing look. In other words, I've cut small, thin slots in it. So putting it on here, it behaves exactly the same way as the other one, backwards and forwards, backwards and forwards. Okay. Let's see how much braking effect this one would have. So putting it in here, same distance away. And we notice that it's not coming to a halt anywhere nearly as quickly. It is coming to a halt, but it's taking a much longer time to do so. Okay, now it's coming down. And the reason being, in this case, we still have eddy currents induced in the tines of this comb here, but the size of the eddy currents is as large as the width of each of these comb tines here. So we've reduced the amount of eddy current because we've got the available space has been reduced as well. This is the same as lamination. So by laminating a core of a transformer, we reduce the area in which an eddy current can be forming. And you would have seen on the big video this whole idea of dropping a magnet through a slotted tube, and this would be like the slotted tube. The amount of eddy currents as the magnet goes through the slotted tube would be minimized because they can't actually be large eddy currents and larger currents. So just to recap, if I use this one and without anything at all, I get normal pendulum motion. Then if I was to put the magnetic field in there, I get really quick braking effect, and that's because the eddy current is quite large. Putting in the putting in the slots, I still have a braking effect. It's nowhere near as long as the without the slots. It's coming to a halt. It's much longer, but it still comes much quicker than if there was no magnetic field there at all. Okay, I hope this makes sense for you. I'll see if I can make this tilt around. Otherwise, watch this by lying your head on a pillow. Okay, bye.